Hello, in this lesson today we will talk about nuclear binding energy and liquid drop model. I have used several books while preparing this talk. Mainly I have used the book of Kaplan, Nuclear Physics by Kaplan, then Nuclear Physics by K.S. Crane, the Nuclear Physics book by S.N. Ghoshal, and several other books. And the following papers, the first paper is by George Gamow, 1930, then Bohr and Kalakar, 1937, then Von Weizsäcker, 1935, Bethe and Batcher, 1936. So to begin with, let us first set up the scale. So the scale is set by 1 mole of carbon. We know that 1 mole of carbon weighs 12 grams and 1 mole contains Avogadro number of atoms. Mass of 1 carbon atom is 12 grams, that is 12 multiplied by 10 to the power minus 3 kgs divided by the Avogadro number n0. So that is the mass of 1 carbon atom. So per nucleon, the mass, if you want the mass per nucleon, then we have to divide by 12, and after dividing by 12 and the Avogadro number, here we get 1.660566 multiplied by 10 to the power minus 27 kg. Here is the 10 to the power minus 3 and Avogadro number has 10 to the 23. So naturally 10 to the minus 26 here, and then there is a division by 6.02205. So finally we get 10 to the power minus 27 kg for 1 unified atomic unit. In older books we find atomic mass unit AMU, which used oxygen atoms as the reference. So oxygen has 3 isotopes, O16, O17 and O18, and they are found in the proportion 99.76 is to 0.04 is to 0.20. So we can make a weighted average of the mass of oxygen atom of 3 types, 3 different isotopes, and then divide that by 16, which is the predominant isotope. So then that will be slightly larger than 1 unified atomic unit. An atomic mass unit will be slightly more, so that is 1.000317 U. Then binding energy is the difference. Suppose you have an atom which has Z number of protons and N number of neutrons, and you measure the mass of that atom to be MaZ, total mass. So the mass which is remaining, that becomes the binding energy using Einstein's mass energy equivalence. So here is MP, which is not exactly an integer, slightly different from an integer. So we can say 1 plus Fp. Similarly, Mn is also slightly different from unity. We can call it 1 plus Fm minus MaZ. So 1 plus Fp, this sum is MP because it is slightly different from 1. 1 plus Fn, this sum is Mn because Mn also is slightly different from 1. Then it is easy to simplify this expression by taking Z from here, N from here, so Z plus N, and then ZFP plus NFN, ZFP plus NFN minus MaZ. So rearranging, we get ZFP plus NFN coming from here, minus within bracket MAZ minus Z plus N is A. So MAZ minus A. Then if we find binding energy per nucleon, that is EB by A, then we get from here ZFP plus NFN by A minus, from here we get delta M. So it is slightly different from an integer. Is A is Z plus N, and that difference divided by A, that is A is our sum of Z and M. This quantity we call the packing fraction, and this is all known. Z is known for a given atom, Z is known, N is known, Fp and Fn are known to be 0.007825. that is how much Mp differs from unity, and 0.008665, that is the amount by which Mn differs from unity. This is a known quantity, and this is the packing fraction. So binding is closely related with the packing fraction. But when packing fraction was defined by Aston, at that time the atomic model was different. At that time it was believed that the nucleus consists of protons and electrons. So protons contribute to the mass, and electrons contribute a certain amount of negative charge, so that we get the observed charge for the nucleus. But later when atomic model was established, then it was easy to have a correspondence and physically understand the relation between the packing fraction and binding energy. We will discuss it a little bit more later in the transparencies. So why is it important to measure atomic mass so precisely? That is very natural, because atomic masses need to be measured with great accuracy for the calculation of nuclear binding energies and disintegration energies, because these tiny differences in mass can lead to a great difference in energy by the relation E equal to mc square, because C has such a big value. That means we have to measure the masses very accurately. It is a very important problem. So this problem was attacked first by Aston, Francis Aston, and what he did is that he used ions, then used that ionized beam through a velocity selector. What is a velocity selector? In a velocity selector, in an inhomogeneous beam, that beam will contain in general ions of many different velocities, right? So then we have to select a particular velocity before it goes to the measurement chamber. So how to do that? You apply electric field and magnetic field. Magnetic field is perpendicular to the page of the paper, and it is going towards the page of the paper. Then you see, then V cross B, if you use V cross B, then the force will act upwards. So V cross B, from V to B, if you go using a right-handed corkscrew, then the force will act upwards, and then electric field you put downwards, and you use positive ions. That means electric field will be downwards. So that means for a particular velocity V, this upward force, magnetic force and the electric force can be balanced. Other ions will deviate to the left or to the right and they will be blocked. So when this velocity selector is crossed, then ions have a specific velocity, say v. Then with that velocity it goes to this chamber. When it is again in a magnetic field, it is put in a magnetic field, and then it traverses a semicircular path. We can measure the radius theoretically, and also we can measure the radius here. So putting the value of r here, q and b are known, then we can calculate the momentum of the ion. So if you know the momentum and you also know the velocity, then you can determine the mass of the ion. So this type of mass spectrometer, Aston worked on this for many years, Francis Aston, and he finally was able to develop a mass spectrograph which could measure the masses of nuclides up to accuracy of 10 to the power minus 6 accuracy. So delta m by m is 10 to the power minus 6, a very great precision, and he mainly used it for the measurement of the masses of isotopes, and he was awarded the Nobel Prize in Chemistry in 1922. This is a very important part of this work because it will go into this expression here, and that is how we will calculate the binding energy. The binding energy will depend on the mass, so the mass has to be measured very accurately. So even further accuracy can be obtained using a penning trap. A penning trap is another machine, another type of setup, experimental setup, where the ratio of cyclotron frequencies of two particles of different masses but same charge and in the same magnetic field is equal to the ratio of the masses of those ions. If one of the masses is known by from the ratio, the other mass can be determined very accurately, and this accuracy can go up to 1 part in 10 to the power 10. So that is delta m by m is 10 to the power minus 10. And for this type of work, H. Demelt won the Nobel Prize in Physics in 1989. It is important to measure the masses of microscopic particles in general, the masses of leptons or the masses of proton, masses of neutron, mass of the hydrogen atom, mass of the helium atom, masses of heavier atoms, for example mass of the uranium atom, thorium atom. All those masses need to be measured very accurately, because finally you are going to insert it here in this expression. Next, we also want to determine the radius of the nucleus, how large or how small is the nucleus, and to do that the experiment which is generally used is high energy electron nuclear scattering, electron proton scattering, and one plots the charge radius. We agree that we can say that charge radius is this is the thickness, the shell which covers the nucleus. So this is a very accurate way of measuring this profile, and from this very accurate graph we can define what we say as R, the length scale of the nucleus. And this was a very important work by R. Hofstadter and for this also he won Hofstadter won the Nobel Prize in physics in 1961. If we measure this R using electron-proton scattering for various different types of nuclei, then finally we can arrive at a relation like this, which expresses R as a function of A, and we know that R is R0 e to the power 1/3. This is a very important relation that we will use in constructing the liquid drop model. This relation will be very important, but note that this is obtained experimentally by actually studying the radius of various nuclides using electron-proton scattering. Next we have to know a little bit about what is the nuclear density. So does it depend on the value of A? Does it depend on the value of Z? Does the nuclear density change from one element to another element? For example, nuclear density in hydrogen, will it be different from nuclear density of iron? Will it be different from nuclear density of uranium? So that is a very relevant question. So to answer this question, let us consider a nucleus with mass number A. The radius is then R equal to R0 e to the power 1/3. That is what the relation we got using the electron-proton scattering. And then the volume is 4/3 by R0 cube multiplied by A. So from here we get R0 cube, and from here cubing this we get A. Now because there are A nucleons, then the mass of the atom is A multiplied by U. U is this unit. So the density will be A multiplied by U divided by this volume. But very interestingly, this A is cancelled here. So that means this rho is not depending on A. Then we can substitute the values of U and pi and R0. We get R0, there is slight uncertain. R0 is slightly uncertain because we are measuring the charge radius and defining R like this. So we have used two different values of R0. One is 1.25 Fermi, another is 1.3 Fermi. Then using these values of R0, we see 10 to the power minus 15, this is minus 45, so it goes up 45, so 45, 27, we see 18, and all these numbers are put in this place, and then calculating this we get 2.03 10 to the power 17 kg per meter cube when R0 is taken as 1.25, and 2.3 multiplied 10 to the power 17 kg per meter cube when R0 is taken as 1.3 Fermi. So this is a very, very high density and also very striking. And another striking thing is that it doesn't depend on the element you are seeing, because A has cancelled out. So this is a universal value for rho. So we notice that A has cancelled from rho. This means that rho has an universal value. We should also remember that even though we call it mass density, we should actually call it mass energy density, because mass and energy are equivalent using E equal to mc square. Mass energy equivalence. We can also have a feeling of how much was the energy density of the universe when the universe was near the Big Bang, when the atoms and molecules were not formed. and the universe existed in the form of a very dense soup of nuclear matter. So the whole universe was consisting of nuclear matter, and the size of the universe was much smaller. And there are various theories of how the size of the universe grew from a small value to a very large value. And when the size of the universe grew, then slowly the atoms and the molecules were formed. And so atoms and molecules, the densities will be much smaller than the nuclear density, of course. But this is another story. Perhaps we will talk about this nuclear matter in early universe in a later sometime in another talk. But these are very related. That when you see such high density, 2.3 10 to the power 17 kg per meter cube, immediately you think about the primordial values of density, energy density, when the universe was in its early stage, so early universe, this kind of values were prevalent. Next, let us talk about this Prout's hypothesis. Prout, as early as 1816, so that is 200 years ago, on the basis of a small number of atomic weights which was known then, Prout suggested that all atomic weights are whole numbers, and they are integral multiples of the atomic weights of hydrogen. But this hypothesis was not supported by the scientific community when it was found that chlorine has atomic weight 35.46 and copper has atomic weight of 63.54. At the time, the existence of isotopes were not known, so this type of fractional atomic weights were found by chemical processes, chemical ways of determining. So Prout's hypothesis, which was very close to truth, was somehow was not supported for the next 100 years. Then Aston was working in this was early 19th century. Aston was working early 20th century, so he formed a revised version of Prout's hypothesis when he says the whole number rule. The whole number rule is very interesting. According to the whole number rule, all atomic weights are close to integers, whereas fractional atomic weights like this 35.46 and 63.54, these are fractional atomic weights are determined by chemical methods, which are determined by chemical methods are caused by the presence of two or more isotopes which have masses close to integral values. So those individual isotopes, their masses are close to whole numbers, but in chemical means, in biochemical process, when we define atomic weight, we see an average value. But Aston was working with mass spectrographs, so he could determine actually determine the difference in the masses of isotopes. So then he found that there are two different masses which are whole numbers. So it was called two isotopes, two or three isotopes. For example, oxygen has three isotopes. And by chemical process, when you find the atomic mass, then you see a fraction. So that was a major breakthrough, because in the mass spectrograph, Aston had that power to look at the difference of the masses of two isotopes. So this whole number rule is valid for one part in 1000. So that means delta m by m is 10 to the power minus 3. And Aston also found, because Aston had the accuracy of 10 to the power minus 6 in his mass spectrometer. So what Aston found, he could also study the deviation from his whole number rule, and though he could not give a rule of why this deviation is occurring, he saw and he plotted that this deviation from the whole number rule is very systematic. He plotted the variation from the whole number rule, and it was seen that this variation is very systematic. But unfortunately, at the time of Aston, the nucleus was thought to be made of proton and electron, so he could not give the exact physical significance of why the packing fraction is varying in a systematic manner. But fortunately, in 1932, James Chadwick found the neutron. So once neutron was found, then the picture of the atom was changed. It was previous to Chadwick's discovery, there used to be protons and electrons. But after the discovery of Chadwick's neutron, it was much simplified. So then neutron was a neutral particle. So for example, if you want to have a mass of 5 and charge of 3, you would say there are 3 protons and 2 neutrons. There are 5 particles inside the nucleus. So it gets simpler, and 2 electrons, then the value of the spin will be different. So it is also easier to it is also possible to explain nuclear spin in a theory which thinks that the nucleus is made up of proton and electron rather than proton and neutron rather than proton and electron. So once we have this picture of then we can define this packing fraction as this mza minus a by mv, and we have a clear picture, physical significance. From here we know that the packing fraction and binding energy, it is clearly there is a relation. So with this precise determination of the masses, proton, neutron, and the masses of elements, nuclides of elements, then binding energy for each element can be determined experimentally, and we can have a plot. We can have a plot like this. See, I have plotted the packing fraction and I have plotted the binding energy plot curve. So binding energy curve has this feature that for the lower values of Z, it rises up very sharply, and then it reaches a maximum of 8.8, and from that portion, from 8.8, it slowly reduces to about 7.6 MeV. So highest point is about 8.8 MeV, and this portion is fairly flat, and this portion is fairly sharply, it rises and becomes fairly flat. So this shows that the binding energy has a saturation. So this property is the saturation property, that binding energy is getting saturated. This is the value of 8. We see same type of it doesn't differ much, 8.8 to 7.6. So it means that the nucleons, the forces, they are interacting with its close neighbors, and so that shows some kind of saturation. Nuclear forces, they are between the close neighbors, not that means one nucleon doesn't interact with all other nucleons inside the nucleus, but it interacts with its immediate neighbors. That shows that nucleons are basically they are happy with interacting with their close neighbors. So that is the saturation property. Then the point is how to explain the shape of this curve of the binding energy of nucleon, and is it possible to have some insight into what are the contributions to this energy? Is there a contribution from electromagnetic contribution? Is there any other contribution? So this must be an aggregate value, and this binding energy must have come from various component by component. Perhaps we cannot understand the binding energy fully, but certain average properties of nuclear forces, such as the saturation property or short range property. So some properties of nuclear forces which have been deduced from an approximately linear dependence of the binding energy and volume on the number of particles in the nucleus are analogous to the properties of the forces which hold together a liquid droplet. This idea, along with other classical ideas such as the electrostatic repulsion and surface tension, are used to set up a semi-empirical formula for the binding energy of the nucleus in its ground state. So it doesn't actually give you the full quantum mechanical picture, because in quantum mechanics you will not have a single curve. So each nucleon will have various energy states. So this will really not be the quantum mechanical pictures, but what the binding energy curve, the liquid drop model, the semi-empirical mass formula, which is semi-classical, it tries to generate this curve, binding energy curve, binding energy of the nucleus in its ground state, only. So since the volume of the nucleus is proportional to A, because R is proportional to A to the power 1/3, a contribution which is proportional to volume is also proportional to A. So a volume contribution will be proportional to A because volume itself is proportional to A. So that is, volume contribution EV is AV multiplied by A. Then there is a Coulomb repulsion between the protons. There are protons and neutrons. So there are electrostatic repulsion between the protons, which will reduce the binding energy. So suppose they consider one proton, it will interact with Z-1 protons and the energy will be Z-1 by R. R is the typical nuclear radius. But there are Z of them, Z protons, so Z-1 by R has to be multiplied by Z. So finally we get Z into Z-1 by R, or this Coulomb energy is proportional to Z into Z-1 by R, or the Coulomb energy is, this is a way of writing 4AC, but you can write simply AC. This is a notation used by Kaplan, but this minus sign is important because it reduces the binding energy. So minus Z into Z-1 divided by R. R is A to the power 1/3. So here we get proportionality of A. Here we get a proportionality inversely proportional to A to the power 1/3, and also it is directly proportional to Z square. This is a z square dependence, and there is also linear dependence on z, but we will see that because this is very small, coefficient will be very small, so dominantly it is a z square dependence. The Coulomb energy dominantly depends on z square by r. So when counting binding energy, we have say volume energy. When counting binding energy, we have overestimated contributions coming from nucleons which reside on the surface of the liquid, because on the surface there are certain nucleons which are on the surface and they are not interacting with all the sides, so they are interacting with nucleons which reside inside the surface. So in some sense we have overestimated the contribution. In this formula we have overestimated the contribution of nucleons which reside on the surface, so that amount has to be subtracted from the binding energy, and so that should be proportional to r square, because the area of the sphere depends on r square. So that is a to the power 1/3 square. A to the power 1/3 square is a to the power 2/3. A to the power 2/3, and so E is equal to minus A is a to the power 2/3. Why minus? Because it reduces the binding energy, because this has overestimated the binding energy, so we have to subtract out a correction which is proportional to the surface area, which is proportional to a to the power 2/3, because the radius is proportional to a to the power 1/3, so surface is proportional to a to the power 2/3. So that is the surface term of liquid drop model. So this is volume term, this is Coulomb term, this is surface term. Next we have a symmetry term. What is a symmetry term? Let us try to understand. This dependence of a minus 2z whole square by a. So let us try to explain this. So if z number of protons and neutrons are equal, then z is just half of a, so this will become 0, so it will not contribute something. This part will not contribute if protons and neutron number is same. So it is a minus 2z, but we see that for very large values of a, this effect reduces. This is experimentally found. These are why a minus 2z whole square, because then it will not only vanish if a equal to 2z, but its derivative, for example del E or dz, what will it be? It will have a factor of a minus 2z, so that will also vanish when a equal to 2z. So that is called the symmetry term. So if z is a by 2, then this will not contribute, but if z differs from a by 2, it will have a negative contribution to the binding energy. Next we see the odd-even effect. What is odd-even effect? Let us see the number of stable isotopes. Out of 272 isotopes which are stable, we see 164 of them have even type, that is even number of protons and even number of neutrons, and only 4 of them has odd number of protons and odd number of neutrons. So that means if you have even number of protons and even number of neutrons, then binding energy is large, then we find them stable. If there are odd number of protons and odd number of neutrons, then binding energy is less, so there are only 4 of them. But if in the even odd or odd even case, even odd case, odd even case, we see say 50 of them. So totally we see 104 of them. So that means the binding energy contribution is somewhere in between. So there is a large contribution when protons and neutrons both proton number and neutron number are both even, and there is a negative contribution when both of them are odd, and suppose there are no contribution when either the proton number is even, neutron odd, or proton odd, neutron even. So in those cases, let us say we do not have any contribution from the odd even effect. Okay, so that means we can say something like this: for even cases there is a positive contribution, for odd cases there is a negative contribution, for even odd even cases there is no contribution from the odd even effect. So this is not delta by 2a, this is from Kaplan, but in modern cases, in modern books, you will see this contribution is parameterized in terms of a to the power in the denominator a to the power 4/3 instead of a. So obviously then this value of delta will be different, but we will see in the next transparency for various authors how do they parameterize this odd even effect. But the physics, let us try to understand what is the physics, why it is happening that for even cases, and what is happening for odd cases, and what is happening for even odd or odd even cases. So let us try to understand. So this comes from a pairing energy. So there must be a pairing energy term which arises due to pairing of nucleons of the same type, let us say 2 protons or 2 neutrons, but with opposite spin. Such pairing increases the nucleon, increases the strength of binding energy, which becomes maximum for even nuclei. Why? Because for even nuclei, all the protons will be paired, because it's a even number, it is divisible by 2. And also all the neutrons will be paired, because neutron number is even, which is divisible by 2. So that means all protons and all neutrons will be paired. In the even odd type nuclei, the proton is even, odd neutron is odd, so all the protons will be paired, but not all neutrons will be paired. There will remain one unpaired neutron. In the odd even type, all the neutrons will be paired, but for the protons, all of them will not be paired, because there will remain one unpaired proton. So either one unpaired proton or one unpaired neutron, which will weaken the binding energy by few MeVs. And in the odd cases, neither the proton or not the neutron, they can be fully paired, because both of them are odd. So there will be 2 unpaired nucleons, 1 unpaired proton and 1 unpaired neutron. So 2 of them will remain unpaired. So binding energy of such a nucleus will be further weakened. So it will have a negative contribution. This coefficient will be negative, and this coefficient will be positive. How it looks exactly. So let us say this is E delta plus. Then for even cases, the binding energy will increase, and for odd cases, binding energy will decrease. But if you say this is minus, then this will be minus, this will be plus. So it depends on how you define the overall sign of E delta. So finally the binding energy is this is a volume contribution, this is the Coulomb contribution, this is the surface contribution, this is the symmetry contribution, this is the pairing contribution. So there are 1, 2, 3, 4, at least 5 coefficients has to be determined from experimental values, but you see that there are a large number of points in this binding energy curve. There are so many points, so it depends on which points you prefer while you do the fitting of the data, and from there are certain differences from author to author. In various papers you find slightly different values of these coefficients. This is mainly because the points which are picked up for fitting, they have picked up different points of the binding energy curve for their fitting process. So let us have some idea. Let us say this case grains. You see that this, so Coulomb term is really small. Coulomb term is really small, so you can actually approximate it as z square. So if you suppose S.N. Ghoshal is giving it in terms of U, not in MeV. So here you see that the Coulomb term is really 0007. So we have, instead of writing z into z minus 1, he has just neglected that linear term z square. So this is the typical semi-empirical mass formula after you have done the fitting of data points. Once you fit the data points, then you know the coefficients. So this is known as the semi-empirical mass formula. So let us try to see one application of semi-empirical mass formula, which is seen in all standard textbooks. So this is the stability analysis of beta minus and beta plus decays. So for that we recast that mass formula in this form, where Fa, this part is independent of Z, this part linearly depends on Z, and this part quadratically depends on Z. And you can easily write down what is its coefficients. Then this is M, and then minimize del M del Z equal to 0. So if del M del Z equal to 0, you get a relation Z equal to minus P by 2Q. Minus P by 2Q. So minus P is this. So Mn minus Mh plus 4F4 divided by 2Q. This is 2Q. This is 2Q. So A goes up. This A goes up. A by 2 into this. So this is the value of Z when A is fixed. When A is fixed, you have different isobars. The different isobars are related by beta decay and beta plus decay. So different among different isobars, there will be one value of Z which is more stable, and so in a isobar multiplet, there will be a tendency to decay to a specific value of Z, which is ZA, and we can calculate it from the semi-empirical mass formula using this mass formula. So that is one of the success of the semi-empirical mass formula. So we can say that yes, we are in the right path because we can do the stability analysis of isobaric multiplets under beta plus and beta minus decays. So this was our formula MAZ, and if you put the value of ZA, then here is a ZA, and we see that ZA is minus P by 2Q. So we get minus p square by 2q, and here p square by 4q square, 1q cancels, then this is p square by 4q. So finally, coupling these two terms, we get fa minus p square by 4q. This is maza. So if we subtract maza from maz, then we get fa plus pz plus qz square minus fa plus p square by 4q. Fa cancels from here, and we can write, we can replace q with okay, so let us keep qz square, then p square, we can keep p square by 4q, and here we have pz, so let us multiply this term with q. So q multiplied by p square by 4q square, so that is z is square, q times z is square. Then in p we can from here we can substitute minus 2qza, so minus 2qza plus qz square. That means here is a q. So let us take a q common, so that is z square minus 2zza plus z square, that is q common again, z minus za whole square. So that is, this difference is minimum when z equal to za. So this proves that there is no difference when z equals. So that is really the minimum point of mass in this isobaric multiplet. So here we have plotted say a equal to 125. So notice, if a equal to 125, then either the proton number has to be odd or the nucleon number has to be odd, because a is the sum of mass of number of protons and number of neutrons. So pairing term will be absent, so then we find a chain like this, and here is the point of minimum. Beta minus decays will bring it here, and beta plus decays will bring it here. And also you can see a even, then there are two cases, either even or odd, because the sum is even. Even sum can be from summing two even numbers or two odd numbers. So for the odd cases, there is a binding energy curve, and for the even cases there is another binding energy curve, and so there will be jumping from odd to even to odd to even, something like this, keeping the value of a fixed. So suppose you start with odd. So by beta decay, you reduce, a negative charge will go out, so a neutron will be converted to a proton. So now the neutron number is even, proton number is also even, because a new proton has appeared. So you jump from odd graph to the even graph. So now say your proton number is even, or neutron number is also even, then you again emit a beta decay. So now the proton number is odd and neutron number is also odd. So again you jump from even to odd. So in this way, you see for when a equal to 128, what are the stable products. Your decay chain will end in these two stable places. So this is and that you find in experiments. So finally experimentally you verify these decay chains, and so you get some kind of confidence that your semi-empirical mass formula is pointing towards the right direction. So here there is another plot it's again from the book of Crane. It's a beautiful book and very well written. So there are these various components, volume, energy, and then when you add the surface term, then it bends like this. When you add the Coulomb term and symmetry term, then it bends like this. So various components, how they behave when you change the mass number. Mass number is plotted here, and binding energy is plotted here. So please see this 3.17, 3.18 figures of case. They are beautifully written book. So today we have discussed nuclear binding energy and liquid drop model, and it is relevant for and its relevance for beta decay and stability analysis, and it has some other applications also. For example, in nuclear fission it is used, but that we will cover in another lecture in this series. So we can stop our recording here, and thank you for watching.